Lab 4, the physics of extreme sports with rope. Using the techniques we have learned thus far, and Newton's second law and the energy principle, we will predict the motion of the ball. This is my rudimentary drawing of a ball on a string with the two forces acting upon it. To use Newton's second law to predict the future, we note that momentum is equal to the mass times the velocity. Therefore, with some algebraic manipulation, we can determine that the change in velocity over time is equal to the net forces on the system over the mass. In this instance, we have two forces, the spring force, which is equal to the opposite of the spring constant times the stretch of the spring, and the gravitational force, which is equal to the opposite of the mass times the gravitational constant. After uploading the video in the tracker, I set the origin at the fixed point of the spring, with the positive y direction pointing up. I also set the calibration stick at 0.70 meters, which was the resting length of the spring. Then I created points of mass as the weight swung. These points of mass created an x and y coordinate for the position, and I copied this data into a CSV file to use later. To compare the model with the observed data, I have input the CSV file into the code. The CSV file is named springmassdata_2D. Using the Python code given to us, I adapted the code to fit our experiment. The mass of the ball is equal to 0.402 kilograms. The starting position of the ball is equal to the vector negative 0.108 in the x direction, negative 0.66 in the y direction, and 0 in the z direction. And that is position in meters. Additionally, the initial velocity is 0 as the object begins at rest. First, we must predict the position of the ball on the spring by looking at the forces on the system. We have two forces acting on the ball. The gravitational force, which has a y-coordinate of a vector, the opposite of the mass of the ball times the gravitational constant, and that is in newtons, and the spring force, which is equal to the opposite of the spring constant times the stretch of the spring times the unit vector of the length of the spring, and this is also in newtons. If we run the program, the blue ball attached to the spring is our predicted model, while the red ball is the observed data as captured by tracker. From this view, we see that they are somewhat close. Note in the visualization, the blue arrow pointing up is the spring force, and the black arrow pointing down is the gravitational force. We can also look at the visualization of the motion measurements from the video analysis. Here we see that there's a close oscillation, but there is a slight deviation between the red line, which is our observed data, and the blue line, which is our model. Next, we will plot the energy changes in the model. There are three types of energy in this system. 1. Gravitational potential energy, which is equal to the mass times the gravitational constant times the change in the y position. Second, the spring potential energy, which is equal to 1/2 times the spring constant times the stretch. And kinetic energy, which is equal to 1/2 times the mass of the ball times the velocity squared. Now we will run the module. This is a graph that computes the model's energy. Note that the yellow line, which is the total energy, is equal to 0 as no energy is gained or lost to the surroundings. If we look at the graph, we note that the red line is the change in the spring potential energy, the blue line is the change in kinetic energy, the green line is the change in gravitational potential energy, and the yellow line is the total energy. Also, the energy principle is satisfied because the energy has been conserved as the change in total energy is equal to the change in kinetic energy plus the change in potential energy. If we try to estimate the period of oscillation of the spring, which is the number of seconds it takes per cycle based on the x and y coordinates in our experiment, we see that the starting x coordinate is negative 0.1077 meters, and it takes approximately 1.43 seconds to get back to that position. Based on the y-coordinate, we started at negative 0.66 meters, and it took about 1.3 seconds to get back there. The estimates are close to the same time, but this may mean that the object was moving at a different x and y velocity, such that the oscillation would not be the same for each direction.